Well, good morning. This is the February 2nd, 2017 edition of the DTM seminar. Our speaker today is Jonathan Tucker. Jonathan is a Deep Carbon Observatory Fellow here. He started his term in November. Previously, he received his bachelor's from UMass Amherst. Amherst College. Pardon me. The competing Amherst universities. And received his Ph.D. from Harvard, where he was a student working with Sujoy Mukhopadhyay, who was also a postdoctoral fellow here. Jonathan has worked on volatiles and noble gas isotopic signatures in the upper mantle. And today he is going to talk to us about mantle heterogeneity, giant impacts, and the origin of Earth's volatiles. Jonathan Tucker.
Thanks a lot, Eric. All right, are we good on the mic? Yep. Okay, so like Eric said, I'm a new postdoc here, and I'm going to tell you mostly about projects that I was working on during my PhD, which was at Harvard, and I spent also the last sort of year and a half at UC Davis. And this is going to be a talk mostly about noble gases, and I'm going to hopefully sort of impart to you kind of some of the really interesting things we can do with noble gas isotope geochemistry. And these the applications are sort of far-reaching and very ambitious, as stated in the title. So I'm going to start with just two sort of simple kind of first-order observations about noble gases in the Earth. And these will kind of serve to frame the rest of the discussion. The first regards helium-3. So helium-3 is a primordial isotope, meaning it's not produced by radioactive decay or anything. So all the helium that's in the Earth was there since the Earth formed. But helium's also not gravitationally bound to the Earth. Helium escapes the Earth's gravity. So it's basically a one-way street out of the solid Earth for helium. It can't go back in. But when we look at places like mid-ocean ridges and hydrothermal vents like this, we do find helium-3 coming out of the Earth. There's not very much. There's only a few hundred moles per year total integrated coming out of the solid Earth. But it's still some, and it's still detectable. So this simple observation is telling us that the solid Earth, at least some parts of the solid Earth, are retaining primitive volatiles. That the Earth has not fully degassed and fully been processed, despite billions of years, of course, of mantle convection and mantle overturns. The second observation regards the stable isotopes of neon. So this is the ratio of neon 20 to 22. So these are also just stable isotopes or non-radiogenic isotopes. And when you look at this ratio in the atmosphere or in the ocean, the value is about 10. But if you look at that value in the solid Earth, in the mantle, it's something closer to about 13. And this is a very large difference in a stable isotope ratio. And this is an important observation because it means that the relationship between volatiles in the atmosphere and volatiles in the solid Earth is not straightforward. You know, if there had been an extensive mixing of these reservoirs, if there has been extensive outgassing and then subduction of neon, these values would become equalized. But they're very different. We know that there are deep volatile cycles. There's a deep carbon cycle and there's a deep water cycle, and lots of people here study these things extensively. But this observation is all I'm saying about this is that it kind of imparts the notion that relationships between the atmosphere and the solid Earth are complicated in terms of the volatiles. So I'm just going to give you a brief introduction to the noble gases and how they work in the solid Earth. So this is my periodic table here. And one of the neat things that attracts us to working on the noble gases is the fact that we've got so many different isotopic systems that we can work with. We have, among the 5 noble gases, we have 8 radiogenic isotopes. Those are isotopes produced by radioactive decay, and a whole slew of stable or non-radiogenic isotopes. Actually, all of these are stable, but sort of stable in this sense means not radiogenic. I'm mostly going to be talking about the radiogenic systems today. So within those radiogenic systems, we've got isotopes of helium, neon, argon, and xenon that are created by radioactive decay of various parent elements. But the reason that the noble gases are unique in this sense is because of the very different geochemical behavior of parents and daughters. So the daughter elements, the noble gases, are atmophile. They, of course, like to be in gas phases, whereas the parents are lithophile. They like to stay behind in the rocks and in the magmas. So because of processes like degassing, you can potentially create enormous parent-daughter fractionations. You can separate parent and daughter elements, and that in time leads to really large isotopic anomalies among the noble gases. So just to demonstrate that the variability of helium isotopic compositions in the mantle is a whopping factor of 10. So this is not the difference between the mantle and the atmosphere or the crust, which are also very large, or even larger actually. This is just the variability of helium isotopic compositions between different domains in the mantle. It's a factor of 10. And factors of a few for neon and argon, and tens of percent also for xenon. So these are really large isotopic anomalies that are created in the noble gases. So there's no delta notation here. There's no epsilon. These are not, small variations. These are large variations. But the problem is that some of them are quite difficult to measure. So in terms of the number of mid-ocean ridge basalts, just as an example, that have been, in my very subjectively defined sense, well-determined, that helium isotopic compositions have been measured for decades, and they're relatively easy to measure. So there are thousands of mid-ocean ridge basalts with well-determined helium isotopic compositions. And neon is sort of getting up there also. In the last maybe 10 years or so, I think we've had the ability to actually start looking at neon isotopes in sort of global senses because of the number of analyses available. But argon and xenon are very, very small. And actually these numbers here include unpublished data, which probably they shouldn't. But so something like a third of these are unpublished. But the point is that the isotope geochemistry, especially of the heavier noble gases, is one of the most data-limited fields in mantle geochemistry. So that makes it really exciting for me to work on. Okay, so what I'm showing in this slide is just sort of a cartoon illustration of how the noble gas isotope ratios behave in the solid earth and how we interpret them. So the example here is going to be with helium isotopes, where helium-4 is produced by, it's radiogenic, it's produced by the radioactive decay of the alpha decay chains of uranium and thorium. Helium-3 is our stable reference isotope. So the way that these ratios evolve in the mantle and the way they're commonly interpreted follows this sort of procedure. First of all, during mantle convection, material is brought up at a mid-ocean ridge where it melts and degasses, and helium is a very highly incompatible element, and it's also insoluble. So the helium basically gets efficiently removed out of the melting column and gets transferred into the ocean and the atmosphere during these normal sort of volcanic processes. But what's left is the uranium. The uranium, of course, doesn't degas. It returns back down to the mantle. So the subducting package is going to have a very high ratio of uranium to helium. It's going to be dominated by uranium. And over time, this uranium is going to decay into helium-4, and this will produce very high ratios of helium-4 to helium-3. So through degassing, you lose all of your helium, but over time you regrow the helium-4. So the interpretation then of helium isotopes is that high ratios of helium-4 over helium-3 represent a portion of the mantle that has been more extensively degassed or processed by these plate tectonic cycles. Whereas low ratios of helium-4 to helium-3, or some people prefer the inverse, helium-3 over helium-4, but I'll mostly be referring to the 4-3 ratio. So low 4/3 ratios represent domains of the mantle that are relatively undegassed or more primitive because they've retained their helium-3. And so this can be shown here with this early histogram of ocean island basalt and mid-ocean ridge basalt compositions. I think this was one of the first compilations to kind of look at mantle reservoirs statistically. And the picture hasn't really changed. The first thing that you notice about this is, first of all, the mid-ocean ridge basalts show a narrower distribution of helium isotopic ratios, which is compared to ocean island basalts, which is also seen in a lot of other isotopic systems. But the other important thing is that ocean island basalts, their range extends to much lower values, much more lower values of the helium-4 to helium-3 ratios, indicating they're sourcing from more undegassed or more primitive reservoirs. And it's observations like these that really led to the development or the idea of primitive mantle, areas of the mantle being relatively primitive. But there's a problem with this interpretation that a lot of people have pointed out, which is that it's really hard to preserve primitive domains in the mantle. So these are just slices from seismic tomographic images where you can see the blue is cold subducting slabs, subducting all the way down into the lower mantle. So these kind of really sort of destroy the notion of a large isolated reservoir in the lower mantle, because it's pretty clear that the whole mantle is participating in mantle convection. So how can we preserve primitive domains in the mantle in the context of full mantle convection? So to address this, a lot of different authors have come up with what I'm sort of calling non-primitive models, which are basically alternative ways to explain helium isotopic compositions that don't require primitive domains to survive mantle convection. And there's a whole bunch of these. What I'm going to show, though, in the next couple of slides is actually a different way to determine the sort of, quote, primitiveness of a mantle reservoir just from xenon isotopes. And this methodology is actually going to be independent of a lot of the constraints or a lot of the requirements of these types of models. Things like the relative geochemical behavior of uranium and helium, which is an assumption made in a lot of these models. So I'm going to show you a totally independent way to determine whether a reservoir is degassed or undegassed, that is totally independent of the helium isotopes. And it's using the xenon isotope. So I have to introduce the xenon isotopes a little bit here. We have 9 isotopes of xenon. This is the second most number of stable isotopes of any element on the periodic table. But the other really cool thing about xenon is that the xenon in the mantle can potentially come from a lot of different sources. And that's what these different colors are showing. So the pink color shows primordial, which means xenon that was there since the accretion of the Earth, basically. Blue could represent recycled atmospheric xenon, that is xenon that has been returned to the mantle or subducted into the mantle. And of course, if the primordial and atmospheric xenon have the same isotopic compositions, we'd never be able to distinguish them. But we don't think that's the case, so we can actually distinguish them. We also have isotopes of xenon that are produced by radioactive decay. So the 4 heavy isotopes of xenon are produced by the spontaneous fission of uranium-238. And spontaneous fission is a minor decay mode, but it does produce isotopes of xenon. And these same 4 isotopes are also produced by the spontaneous fission of plutonium-244. And plutonium is a short-lived isotope, so it has a half-life of 80 million years. So it's only alive, there's only plutonium there producing xenon in the first few 100 million years of Earth history. And lastly, we have the iodine xenon system. This is another short-lived system where iodine-129 decays to xenon-129. And this is an even shorter half-life of 16 million years. So this system is only alive basically during accretion. So one of the really clever things is that we have 3 different radioactive isotope systems within the xenon, producing xenon isotopes, all of which have different half-lives. So we can actually get really strong constraints on events covering the whole range of Earth history just from the xenon isotopes. And actually, I think this is in some ways sort of analogous to lead isotopes, where really the power in lead isotopes has come from the application of multiple systems with different half-lives that, when combined together, really give powerful chronometric data. And a similar thing is true for the xenon isotopes. But what our goal is going to be here, actually, is going to be to take an isotope of xenon, such as, for example, 132 xenon, although you could do it with any, I suppose, and see whether we can deconvolve the xenon 132 that we measure into these 4 different potential contributions: the primordial, the recycled air, xenon derived from uranium fission, and xenon derived from plutonium fission. And I'll show you in a minute why this will help us determine a sample or Mantle reservoir's, quote, primitiveness. Okay, before I do that, though, I just want to give you a quick tour of how we actually, what samples we're actually measuring and how we do these measurements. So the measurements that I've done are primarily on mid-ocean ridge basalts, and to collect them, we go out on a ship like this, the NOR. This was a cruise that we went on in the summer of 2012. And what we do is lower a metal basket like this one, and Rita Parai, who some of you may know, is standing in the way of this photo. We lower this basket over the side of the ocean, drag it along the bottom of the seafloor, and pull it back up on board and hope it is full of rocks. It's a very low-tech method of sampling. And hopefully our basket is full of rocks, like this one was, and here's Charlie being quite happy about this great haul. And we're really excited when we get samples that look like this, that have nice glassy rims, because those are what we prefer to measure. That's what gives us our best data. So what one of these samples looks like, this is a mid-ocean ridge basalt in thick section, and the noble gases in particular reside in these vesicles, which are produced by CO2 exsolution during magmatic ascent. This is a highly vesicular mid-ocean ridge basalt. Most are not this vesicular. But the way that we extract the gases from this is simply by crushing the sample, which makes cracks in the glass, and the vesicular gas is released. And here's a picture of our extraction system and mass spectrometer. So the samples are actually sitting in these aluminum foil-covered crushers back here, and would just actually physically crush them, and the gas gets released into this series of tubes until it makes its way to the mass spectrometer where we measure it. So that's how these measurements are done. Okay, so to remind you, what we're trying to do is deconvolve the xenon isotopes that we measure in these samples into their different contributions. And so I'm not going to actually show you the data or the methodology for how we do this. It's quite complicated and really fascinating. But I'm just going to jump straight to what the results look like. So this is the result of these deconvolutions for mid-ocean ridge basalts and an ocean island basalt from Iceland. And these pie charts are showing the relative proportions of these 4 different contributions. So recycled air is in blue, primordial is in pink, uranium fission derived xenon in yellow, and xenon derived from plutonium fission in orange. And you can immediately see a couple of things. First of all, the vast majority of the xenon, both in the mid-ocean ridge basalt and the ocean island basalt, are recycled air. So even this ocean island basalt, it's not primitive. It's got a lot of recycled material in it, specifically recycled xenon. And remember, I said with regard to those neon isotopes, if there's been extensive mixing between the atmosphere and the mantle, basically the atmosphere would overwhelm the signal. It hasn't quite done that yet with xenon. Most of the xenon is atmosphere, it doesn't entirely overwhelm it. So we still have these other contributions that we can resolve. And by the way, in addition to seeing differences between the stable isotopes of neon, between the atmosphere and the mantle, there are also measurements of non-atmospheric krypton and xenon stable isotopes in mid-ocean ridge basalts. Actually, these are in well gases. Okay. So most of the mantle xenon is recycled air. That's really interesting. Okay, but the second observation, and the one that's more sort of germane to the points, is that is comparing the relative sizes of the uranium to plutonium-derived xenon. So it's basically comparing the thickness of the yellow slice to the orange slice. And what you can see comparing these two samples is that Iceland, the fission xenon, is dominated by plutonium xenon. There's actually a little tiny sliver of yellow that you might not be able to see here. But I think it's actually, the number is 0 with an uncertainty. So there's very little uranium-derived xenon, mostly plutonium. Whereas the mid-ocean ridge basalt has much more uranium-derived xenon. And the reason that we look at this ratio of uranium to plutonium-derived xenon is because, again, plutonium only produces xenon in the first 500 million years or so of Earth history. So what this means is that if you have a reservoir in the mantle that you say 1 billion years ago take and degas this reservoir, you'll lose both the uranium-derived xenon and the plutonium-derived xenon. You'll lose all the xenon. But you still have uranium alive. You don't have plutonium alive anymore. So when you cycle that material over time, that material will only grow uranium xenon. It won't grow any more plutonium xenon. So a reservoir that retains its plutonium xenon is less degassed, whereas a reservoir that has a significant contribution from uranium xenon is much more degassed. So these are telling us that Morbs must have lost much of their early form xenon. And this idea that Morbs from the ratio of uranium to plutonium-derived xenon are more degassed than OIBs is totally consistent with the helium isotopic story. Okay, so I want to talk about one more system in the xenon isotopes for a minute, and this is the iodine xenon system, a very short-lived system. When we look at ratios of iodine-produced xenon-129 to the stable reference isotope 130 in different reservoirs, we actually see big differences in this isotopic ratio. For example, Morbs tend to have high ratios and OIBs tend to have low ratios. And the way this ratio evolves is the same as sort of the helium does, that high ratios reflect a more degassed reservoir, whereas low ratios reflect a more undegassed reservoir. But this degassing with this system has to happen early. That is basically during accretion, because that's the only time you can create differences in this isotopic ratio. That's when iodine-129 is alive. So high ratios represent early degassed reservoirs, and low ratios represent early undegassed reservoirs. Early meaning accretion. But there's potentially another way that these ratios can change, which is through recycling of atmosphere. So the atmospheric ratio plots down here at about 6.5. So maybe these differences don't have anything to do with early degassing at all. Maybe all this is just this reservoir where there's been air added to it that's pulled the ratio down. And of course I showed before that atmospheric recycling is a very important contribution to the xenon in all mantle-derived samples. So maybe we can actually explain this difference just by recycling atmosphere. So to test that, okay, so do these differences in xenon isotopes reflect preservation of early formed reservoirs, or do they reflect differences in the amount of recycled air? To address that, I'm going to show one more plot of xenon isotopes. I've just added an additional isotope of xenon. The axes don't really matter what they are. But in this space, what I can do is actually test the hypothesis about atmospheric recycling. The reason is because, let's say I wanted to explain these low values by starting with the depleted Morb value and adding air to it. Well, what would that do in this space? If I started with the depleted Morb value and added air to it, the composition would move linearly along this line towards the atmospheric composition. But the Iceland value in this space is way up here. So you cannot explain the Iceland plume composition simply by taking the Morb composition and adding air. So we're forced to conclude then that while atmospheric recycling is certainly important, it cannot be the sole difference between the xenon isotopic compositions between Morbs and OIBs. Rather, we require that the 129, 130 differences do in fact reflect ancient heterogeneity. And not only are they created by ancient processes, ancient degassing basically during accretion, but also that heterogeneity, that difference in these 129 xenon ratios that's produced during accretion has survived all the way through accretion and also through mantle convection. Okay, this is the last point that I want to make about the xenon isotopes here, which is addressing the question of where are these primitive domains in the mantle. So what I'm going to show here is actually some brand new data that actually has never been shown in public before. So it's pretty cool. It's almost hot off the mass spectrometer. So what I'm going to show is data for mid-ocean ridge basalts from this region of the mid-Atlantic ridge. Here's Africa and South America down here, and Canada up here. So this is a part of the mid-Atlantic ridge that is pretty normal and actually very boring. There are no plumes nearby. There are no significant geophysical anomalies or anything like that we know of. The nearest plume is the Azores, which is up here, which is more than 1,000 kilometers away. So this is a very normal, typical depleted segment of mid-ocean ridges, which you can see here from the neodymium isotopes and also lanthanum-samarium ratios. These are all less than 1. Typical depleted Morbs. And what do the noble gases look like? Well, these ones over here have argon and xenon isotopic compositions that are pretty typical of mid-ocean ridge basalts. But actually, these ones over here are really, really low. These are very unradiogenic values, less than 7 actually. These are comparable, or actually in some cases lower than values that we find in OIBs, in these so-called primitive OIBs like Iceland and Samoa. And like I said, there's no other sort of geophysical evidence that this would be an anomalous section of mid-ocean ridge. And even most of the geochemistry is pretty commensurate with normal mid-ocean ridge basalts. But the noble gases really look primitive. So what I would conclude preliminarily from this data is that primitive domains like what we're seeing here in the mid-Atlantic ridge need not be associated with known plumes. It's possible that these things are dispersed throughout the mantle somehow. Maybe they're sampled in plumes somehow preferentially, but they might also be sampled in regions of where there's no sort of necessity for plumes. And I think statements like this actually make Peter pretty happy, right?
Yes. Eric is happy to work.
Okay, so I'm going to summarize what I've shown so far. First of all, the uranium and plutonium-derived xenon confirm that the OIB source is more primitive and less processed than is the Morb source. And while the majority of mantle xenon derives from recycled atmosphere, mid-ocean ridge basalts and ocean island basalts still preserve ancient, that is basically accretional heterogeneity. Be restricted to plumes. They might be distributed somehow throughout the mantle. But really to address this, much more data, both on mid-ocean ridge basalts and ocean island basalts is needed. So I'm going to switch gears a little bit now and actually expand on this concept much more now. This idea of early outgassing. So it's this early outgassing that creates differences in 129, 130 xenon ratios. At least that's the hypothesis. And I'm going to ask, is there another way is there other evidence or other consequences of early outgassing that we can actually still see in the mantle today? And the way that you can potentially create early outgassing is via magma oceans. And magma oceans it's a state of the planet that happens during Earth's formation. When you hit the proto-Earth in this illustration by an impactor, in this case a sort of cookie-looking impactor, it's going to smash into the Earth, melt a large portion of the Earth, and a molten Earth will degas because the gases are insoluble in the magma. So we can potentially create early outgassing through processes of magma oceans. We think that magma oceans probably happened on early Earth during accretion, but is there actually evidence for their existence? And if there is, can we actually use that evidence to talk about the nature of these magma oceans? So, first of all, what creates a magma ocean? Magma oceans are created by giant impacts. And this is going to be a simulation of a giant impact, actually very similar to the ones that Mickey showed the other day in her talk, if you were there. What it's going to show, I don't know why this doesn't start at the beginning. Can I pause it? Okay. Well, so what's happening is that you have an impactor that's going to smash into the proto-Earth, and it's going to completely disrupt the Earth. And this is what it does. These are incredibly violent events during accretion, but this is one of the major ways that the planet forms, by adding objects to it, essentially. But these are very violent events. After a couple hours, you can see that the Earth pretty much returns to its spherical shape. Can I play this again? So these are incredibly violent things. You create a crater that's the diameter of the entire Earth itself. And the reason that these are, one reason that these are important events is because of the consequences that they have on the Earth. So they create magma oceans. These giant impacts create magma oceans. And the magma oceans basically form by decompression of the passing shock waves through the planet. They melt large portions of the Earth, perhaps even the whole Earth. But they're also important for the Earth itself because through magma oceans, this is how the major parts of the planet are formed. Core formation happens basically via exsolution of metal and silicate in magma oceans, and then the metal falls down to the center. The mantle forms by crystallization of this magma ocean, and you also have the potential for extensive outgassing and transferring of the volatiles out of the mantle into an atmosphere. But what's the evidence? What is there evidence that these things actually existed, and is there evidence still existing today? And I'm going to argue that yes, there is, and this is in the evidence comes in the form of the ratio of helium-3 to neon-22. So helium-3 and neon-22, these are both primordial isotopes, noble gas isotopes, so there's no radioactive decay in this system at all. But when we measure this ratio in mid-ocean ridge basalts, what we see are things like this. We see mixing arrays. And what these arrays allow us to do is define the depleted mantle end member. So if you look at this helium-neon ratio against things like lead isotopes for the neon isotopic composition, or also like strontium or neodymium, it would look similar. That this mixing array points towards a depleted end member that has a very high helium-neon ratio. So these high helium-neon ratios are kind of intrinsic to the depleted mantle, and that's what we define using these correlations. On the other hand, ocean island basalts, these primitive ocean island basalts, places like Iceland and Samoa, have helium-neon ratios that are much lower at the other end of the spectrum. So our question is going to be, how do we create these large differences between mid-ocean ridge basalts and ocean island basalts, but also how do we get to any of these values from possible terrestrial starting values? So we don't necessarily know where the Earth's volatiles came from. They could have come from multiple sources, in fact, but all of the potential sources of Earth's volatiles have helium-neon ratios that are very low. Lower than, the highest is about 1.5. So we need to explain how we can get from at most a value of about 1.5 to these relatively low values that we measure in primitive plumes to the much higher values that we measure in the depleted mantle. And this is actually kind of a really sort of interesting observation if you think about this ratio, right? What this is saying is that the mantle, both the primitive mantle but also the depleted mid-ocean ridge mantle, have higher ratios of helium to neon than do any primitive components, including the sun itself, the most sort of helium-rich object in the entire solar system. So that's really interesting that it seems like the mantle, the Earth, would have more helium than does even the sun. Because, again, of course, helium should leave the planet, not the other way around. But I think actually one of the most important things that I learned in my PhD is that there are always two ways to read a ratio, right? So this doesn't necessarily mean that the Earth is enriched in helium-3, but maybe it actually means that neon is lost in preference to helium during some kind of process. That in fact the Earth is depleted in neon as opposed to enriched in helium. Okay, so I'm going to hypothesize that this extreme fractionation of helium and neon takes place through magma ocean processes. And in explaining how that works, I'm going to show a couple of cartoons that look sort of like this, where we have some section of the mantle that's going to have a high helium-neon ratio and some section that's going to have a lower helium-neon ratio, but I'm importantly going to say that these are just cartoons. The reservoir sizes and shapes are not to any sort of scale. It's just drawn this way for convenience. Okay, so the way that we're going to be able to increase the helium-neon ratio in the Earth is going to have to do with magma ocean and atmosphere equilibration. The reason this can change your helium-neon ratio is because helium is about twice as soluble in magmas as neon is. So if you dissolve gases from an atmosphere into a magma ocean, or if you outgas from a magma ocean to an atmosphere, basically if you have equilibration between an atmosphere and a magma ocean, the helium-neon ratio in the magma ocean is going to be twice that of the atmosphere because it's twice as soluble. So what we propose is the following sequence of events. This is kind of going to be a minimum sequence of events that will be able to explain our helium and neon data. And the first step is going to be nebular ingassing. This is happening during accretion, probably not on the Earth itself, but on the smaller objects that later accreted to the Earth. Once an object is large enough, it can gravitationally accrete solar nebular gases. And so these gases will form a nebular atmosphere. A thick atmosphere can also sustain a magma ocean underneath it. And these gases are going to dissolve into the magma ocean. And because helium, again, is twice as soluble as neon, the helium-neon ratio in the magma ocean is going to be higher than the initial helium-neon ratio of the atmosphere. And then when you solidify this magma ocean, you lock in this ratio into the body. So that can potentially explain how we get from these low values, such as the solar nebula or various meteoritic values, to the not quite as low, but still low values that we measure in ocean island basalts, in these primitive ocean island basalts. But we still need to get all the way out to the depleted mantle value. So to do that, we require multiple episodes of magma ocean outgassing. So the way that's going to work is now we're during the main phase of accretion, which is also sometimes called the giant impact phase of accretion. You have a giant impactor coming in, sort of like the one that I showed in that cartoon. In that movie, actually, that simulation. This giant impactor ejects the atmosphere that's overlying the planet and creates a magma ocean throughout part of the mantle. This magma ocean then outgasses, and because neon, again, is more insoluble, it outgasses more strongly, and the helium-neon ratio residual in the magma ocean is increased. So doing this once doesn't get us far enough. It only can get us up to about a value of 5. We need to get up to a value of 10. So we've got to do this process again. So we need another giant impact, maybe the moon forming impact, comes in, again ejects the atmosphere, creates a partial mantle magma ocean, which outgasses again, forming another secondary atmosphere, and inducing another step of fractionation of helium and neon, such that we now get values high enough that we measure in the depleted mantle today. So using this repeated step of this process of repeated magma ocean outgassing, we can explain how we get from primitive values all the way up to the high values that we measure in mid-ocean ridge basalts. So put all together, that's summarized here. First of all, ingassing is explaining the relatively low helium-neon ratios that we measure in primitive plumes, whereas multiple episodes of magma ocean outgassing explain the high helium-neon ratios in the depleted mantle. But there are also two other important aspects of this sequence of events. One is that we require these atmospheres to be lost. The reason is because if we didn't have atmospheric loss, if there were still the old atmosphere over here, this magma ocean would not outgas. It would already be in equilibrium with that atmosphere. So basically, in order to increase this helium-neon ratio multiple times, we need essentially an open system kind of behavior. So we need to have atmospheric loss. And for kind of simplicity, I've had the atmospheric loss be associated with the giant impacts themselves, though this need not be the case. Atmospheric loss could happen by other processes as well during accretion. And secondly, the other important point is that magma oceans could not have homogenized the entire mantle. If you have a magma ocean that's extending all the way throughout the mantle, the whole mantle would be red, it would all be subject to outgassing, and the whole mantle would increase to these high values. But the fact that we preserve primitive, these lower values that we measure in primitive plumes requires that some part of the mantle did not homogenize during these giant impacts. And this is one of a couple of lines of evidence for these sorts of requirements. Another, of course, is the xenon isotopic compositions that I talked about in the first half of the talk, where the 129, 130 xenon ratios are basically created by perhaps these same outgassing episodes, but it's not the same throughout the mantle, so some part of the mantle had to have been protected from that. And there are also now observations of tungsten isotopic compositions, probably resulting from accretion, that also appear to require that the whole mantle did not homogenize during accretion. So this is actually a pretty strong constraint on the nature of these giant impacts and magma oceans. So to kind of put that into a context, these are sort of, I guess, the classical constraints on the nature of the last giant impact, that is the moon-forming giant impact. First is that impact has to match the Earth-Moon angular momentum, has to explain the fact that the moon basically doesn't have a core, and also the fact that the Earth and the moon look very similar or identical, essentially, in isotopically. And this is sort of traditionally, I think, the most difficult one to actually explain with sort of canonical moon-forming giant impact models. But I'm actually going to add two additional constraints to this now. First of all, we require from our helium-neon data, as well as the xenon isotope data and things like the tungsten isotope data, that the giant impact did not create a magma ocean that homogenized the entire mantle. And so as the geochemists were just saying that we think this is a very strong constraint, and then we'll rely on people like Mickey to tell us how this can actually happen. We also, in this model, require atmospheric blow-off, or atmospheres, to be lost. And I've put this in parentheses because atmospheric loss can happen during giant impacts, potentially, but in this model, it just has to happen. It can happen also by other mechanisms. Okay, so I'm going to turn a little bit now to the major volatiles in my last couple of minutes, and explain how these accretional processes could potentially be affecting the major volatiles, things like carbon and hydrogen and nitrogen. And these are, of course, the volatiles that are important for life and making our planet nice and habitable. And this is really asking the question, you know, why does our planet look like this as opposed to something like this or like this? A major question regarding Earth's volatiles is going to be, what is the origin of Earth's volatiles? And this is an important question because during accretion, when the planet's formed, there's this concept of something called an ice line, which is basically, in the inner solar system, it's too hot to condense water into ice, onto solids. So the inner solar system should be very dry, whereas icy or wet objects would form in the outer solar system. And in order to get volatiles then to the Earth, they have to be delivered into the inner solar system at some point. And there's a lot of debate as to how and when this happened. So actually, another important point is not just what, but also when is the origin of Earth's volatiles. Basically, did the Earth form wet? Were the volatiles there during the main phase of accretion? Or were they brought late, after accretion was done, in something like a late veneer, which is something that has been discussed for many decades. So in terms of what is the origin of Earth's volatiles, it's useful to look at a plot like this, where I'm showing the isotopic composition of Earth's volatiles. This is the deuterium to hydrogen ratio and nitrogen isotopic ratios, where the Earth plots over here, right in the middle of this large field of meteorites. So comets plot up here, the solar nebula plots down here, so it really looks like Earth's volatiles come from meteorites in terms of their isotopic compositions. But their elemental compositions are not chondritic, not meteoritic. If you look at the ratios like the nitrogen-hydrogen ratio especially, the ratio in the Earth is very, very different from chondrites, by about a factor of 10 or so. And this is kind of a mystery, potentially, as how this could happen. And by the way, this is also true of other volatile elements like the halogens and the chlorine-fluorine ratio. And this is actually the same, another manifestation of the same thing that Kay showed last week, where there was sort of an upward spike in the abundance of fluorine. This is showing the same thing, but in the opposite way, as sort of a deficit of chlorine. So if Earth just simply accreted meteoritic volatiles, these ratios should be about 1 in terms of the major volatile element ratios, carbon, nitrogen, hydrogen. There's a lot of uncertainty on some of these, like carbon. Oh, and by the way, if you were at my AGU talk, which a couple of you were, I talked much more about the carbon content of the Earth and how this might actually be quite a bit more uncertain than we sort of think. And it's also something that I'm planning to work on here much more extensively. But the observations, especially for things like nitrogen, the helium-neon ratios, specifically things like atmospheric loss. So to explain these observations by atmospheric loss, you just have to think about where these elements go in the aftermath of a giant impact, or during accretion, basically. So nitrogen is a very atmophile element. It'll be strongly concentrated in the atmosphere. Hydrogen, on the other hand, is going to be concentrated in an ocean. So if you lose atmospheres during accretion, which was a requirement of our model for the helium-neon data, you'll also lose nitrogen in preference to hydrogen, thereby bringing this ratio down. And the important thing about this is that it requires that these volatiles are there during accretion, not brought in after accretion. So in order for these volatiles to be subject to loss and fractionation during accretion, they have to be there during accretion. So this is an argument for basically wet accretion, or volatile elements being delivered during the main phase of accretion, as opposed to in the late veneer. And this can also potentially explain these halogens, where chlorine outgasses from magmas much more strongly than fluorine does. Fluorine is a very lithophile element. So chlorine will be concentrated in your steam atmosphere in your ocean. So atmospheric loss and partial ocean loss can also fractionate chlorine relative to fluorine. Okay, so to summarize this second part of the talk, First of all, evidence from the xenon isotopic compositions require differences in early outgassing. But from the helium-neon data, we can show that Earth suffered multiple episodes of atmospheric loss and outgassing associated with giant impacts during accretion. We require in this model that multiple atmospheres had to be lost and that the whole mantle did not homogenize during accretion. And finally, the Earth's major volatiles, nitrogen, carbon, and water, were also shaped by these very same events that are happening during accretion. And that's all. These are my summary figures, and thanks. I'll take questions. Thanks.
Okay, I'm sure there's not very many questions, right? Okay.
So, nice you put this back up. So the percentage of recycled atmosphere in both Morbin and the OIP source is more or less the same. And yet, if the OIP source is undegassed, that means you had to have recycled huge amounts more atmosphere into that source. Right? The proportion of atmosphere to primordial gas is more or less the same in those two pie charts.
It might be a little bit, the amount of primordial might be a little bit higher in this one. What I've also not shown in these pie charts are the uncertainties associated with all of these, which are quite large. There's actually a very small number of samples that the uncertainties are small.
But the point being, if you have an undegassed source and you're trying to overwhelm it with atmosphere, you have to bring in a lot more atmosphere. So that primitive source actually has more recycled material in it than the Morb source.
In an absolute sense, potentially, yeah.
So in terms of calling it primordial, it would not have primordial strontium, neodymium, lead, anything else except maybe noble gases.
And in fact, even in the noble gases, the xenon is mostly not primordial. It's mostly recycled. Yeah, I think that's an excellent point.
Jonathan, go ahead and...
Oh, okay. Sure, Larry.
You mentioned that on the Earth, the magma ocean would be caused by a giant impact. But for the first step of your model here, the nebular and gassing requires that these much smaller bodies also all have magma oceans while it's still a nebula. Presumably they're not all being caused by impacts. Are you just assuming that all bodies of a certain size is original radioactive heating, or?
It could be radioactive heating. I mean, there's certainly evidence from, hundreds and hundreds of iron meteorites that differentiation was pretty common in the early solar system.
But does differentiation require a full magma ocean?
That's a question for a physicist. I'm not sure. So I like in-gassing here for a couple of reasons. It doesn't have to be in-gassing. You could still do this by maybe 3 steps of outgassing instead. Sure. In-gassing also can potentially explain another observation of the neon isotopes, which is that the neon isotopes in primitive domains like Iceland look more like the solar composition than meteoritic compositions, whereas neon isotopes in the Morb source might be more sourced from accreting objects as opposed to the solar nebula itself. Also, by the way, if you look at Mars, the xenon isotopic composition in Martian meteorites looks almost exactly like the solar nebula. So it really looks like in-gassing could have happened, at least on some bodies. And in-gassing is also a good way to deliver a large amount of volatiles to a body. It's not a requirement of this model. I think it fits with the other constraints that we have.
Explain in-gassing.
So in-gassing is just it's equilibration between an atmosphere and a magma ocean. So as opposed to the gases going exalting from the magma ocean into the atmosphere, they're being dissolved into the magma ocean. Yeah.
Kind of along the lines of Rick's question and this conclusion that you have in the lower left that most of your gas is subducted air. I'm just curious how you would distinguish subducted air from contamination. I'm assuming that you crush your samples in a vacuum, but would you be able to distinguish whether you had a contamination or vacuum failure?
So-
account for those large amounts?
Absolutely, that's a great question. And how much time do I have to explain contamination?
Give me a
So,
25-cent answer.
the answer is that contamination is a huge issue, and the main reason that these types of deconvolutions are extremely difficult and can only be done for a very small number of samples. Pretty much every single sample we measure is contaminated with atmospheric gas.
So how do you,
We have complicated mathematical techniques for estimating the amount of gas that is contaminated. It's not a hugely robust thing. We're also doing experiments to kind of see if we can figure out where and why and how atmospheric contamination happens. It could be happening on the ocean floor by assimilation of seawater. It could be happening as you're bringing these samples up from depth. Maybe they, decompress and microfractures form, things like that. Maybe it's happening during sample preparation and analysis itself, maybe some combination of all of those things. So to be able to eliminate it entirely would be incredibly great. But short of that, we have to rely on sort of isotopic tricks to estimate how much and then actually subtract it out. But even when we do that, we still remain with a lot of, and there are also other ways to show that there's a lot of subducted atmosphere.
so those are the corrected?
Yes, these are all corrected. These are not including any contamination.
Okay, but big error bars.
Hmm?
Big error bars.
Big error bars in most cases, yeah. Yeah.
The impact, the giant impact was so strong that the moon has been lost its volatile. Thus, lead was volatilized from it. So today we went to the moon and we found lead to 6 or any lead isotopes. Lead to 6 to lead to 4 on the moon is somewhere between 500 and 1,000 because it's volatilized in the impact. The Earth is part of that impact and much more because of its area. It has been battered orders of magnitude more. Yet, the Earth has a value of 18 or 15. So this is the funny thing. You say the moon is 1,000 or 500 and the Earth is 18. How come the Earth didn't lose any of its primordial lead? And in fact, it is enriched relative to other bodies, like meteorites. So it looks like your story of multiple impacts that creates multiple magma ocean, seems to be working apparently nice in your presentation. However, the lead stands out like a sore thumb.
Yeah.
And we don't know what this dichotomy come from. I don't know.
So I think one important aspect is that even though elements like lead and potassium and other sort of cosmochemically volatile elements will be volatilized on the Earth, they don't escape the Earth because Earth has really high gravity. So even if they're volatilized during the impact itself, they'll be reaccreted to the Earth. To actually lose volatiles from the Earth requires pretty extraordinary events. And in order to do that, you can't really lose volatile elements from the solid part of the Earth. You can lose it from a pre-existing atmosphere if you have atmospheric loss. But lead and potassium and things are not going to be in the atmosphere, they'll be in the solid planet. So I don't know if that answers the question.
It doesn't really. The Earth used to be enriched. This is the
Well, I don't know why it would be enriched, but I think that would...
Look at the lead on Earth is 80% of it is primordial. With our air, somehow it is very difficult sometimes to detect because you are dominated by primordial life.
I have another question about the ingassing stage. Do you know what the size of that body has to be to have sufficient ingassing?
Yes, so there was one paper that calculated this, I think in 1980, and basically the size is about the size of Mars. I think people have told me that those kinds of calculations should be, or would be useful to be revisited, but an important constraint on this is that if you do have ingassing, you need the solar nebula to actually still be there. So that's why I don't think this ingassing can actually happen on the Earth itself. It has to happen on smaller things. But if you're about the size of Mars, you can start to gravitationally attract substantial amounts of atmosphere. Mickey?
So by the journey back, you can remove atmosphere of the planet, but you can also add some volatiles to the planet.
Yeah.
So how would that contribute to your model?
Yeah. So, exactly. Basically, impacts can either add or remove volatiles or both. In reality, it's much more complicated what happens to the volatiles during impacts. And that's kind of why I refer to this as sort of a, quote, minimum sequence of events. In reality, yes, if you add more volatiles to the Earth, you'll actually lower the helium-neon ratio back down. So in order to get it higher, you need to do a process like this maybe more than just 2 times.
Is it possible they have a different helium-neon ratio, or is it possible?
It's possible, but all of the meteorites that we can measure trapped noble gases in today have very low helium-neon ratios, similar to or lower than the solar nebula. Colin?
I think invoking ingassing to explain the high 322 ratio has some issues with it, namely that if you, as you mentioned before, you had the volatility of helium from Earth as a whole system. And so if you have a magma ocean without blowing off the whole atmosphere, the atmosphere that was present prior to the magma ocean will be very neon-rich helium-4. So that ingassing of that atmosphere into the magma ocean then will actually drive the solid Earth in the opposite direction as you suggest here. So I think it's possible for the ingassing process to go both towards higher or lower values. I don't think there's necessarily a bias towards higher values given the different parameters in play.
Yeah, you're right. So you're basically saying there could be helium loss off the atmosphere before you even have ingassing.
Yeah, so then the ingassing drives in the wrong direction.
You could also, well, ingassing would still fractionate helium and neon in the right direction, but the initial value could be essentially 0. You could also lose helium through things like hydrodynamic escape, which has been proposed in the early solar system. So it's definitely a lot easier to go the opposite direction. It's much harder to increase it.
Sure.
Okay, we have time for one more. John Chambers.
Yes, you brought up potassium, which is strongly depleted on Earth and has a similar volatility to chlorine, which you are depleting through atmospheric loss. Does that mean you have to appeal to a completely different mechanism to deplete your potassium?
I left chlorine off that last slide.
Chlorine and potassium are fairly similar volatilities, and yet you're able to remove the chlorine through this mechanism, but you said you can't do that for potassium.
Yes.
So it's just a coincidence that they have similar.
So the dirty truth about this is that I'm far less confident about this part for a number of reasons. Partly, first of all, I don't know how well volatilities of things, especially like the halogens, are really known. But also, not just the terrestrial abundances, but I've also been told recently that the meteoritic abundances of these things are potentially quite uncertain, maybe even by an order of magnitude. So, based on the data that we've got now for the terrestrial and meteoritic abundances, it's a hypothesis that yes, you could explain this ratio by the same mechanism as the major volatiles. Another possibility, though, is that during a giant impact or other atmospheric loss processes, it's actually pretty hard even to lose an ocean. And chlorine will probably be mostly in the ocean. So it's not ultimately clear to me how efficient these mechanisms would be. Maybe you could bring this ratio down a little bit, whether you can actually get it down all the way. So it's possible that there are other explanations for this, certainly.
Okay, let's thank Jonathan one last time.